Technology. Okay, at the end of class last time, we had gotten through, I think, to equation 5, which is distributivity of not over and. You guys have your equation sheets? All right, what do you say we pull them out and continue on? I think just one more session today we'll be all through with what you need to know with, with the paper, and we'll be good to go. And there's going to be a program, there's going to be a homework assignment coming up here in the near future where you'll be asked to prove some of these. So now let's, Oh, is it due Monday? Oh, okay, so good deal. So then, yeah, we'll finish this today and then you'll be all set for that. And then, and now let's recall what was that first unary operator that we learned? The circle, what is that? How do you say that? Next. That's next. And is that all that we got to on our... Actually, that's all we've proved, yeah. And then, okay, so that's all we need to review for that one. And now here is Theorem 6 is distributivity of next over equivalence. Give you a hint here to start with mutual implication. Oh, here's another one. Truth of next. Who wants to start? I'll give you the hint. 3.28, excluded middle. Who wants to start?
I'll start.
All right, so if we do this by excluded middle,
It'll be next, parentheses, P or not.
Next, parentheses, P or not P. Shane, what do you think? What's obviously the one that we should use? Just okay, next P or next not P is correct. Danny, can you think of what we would want to use next? Or shall I give you the hint here? I'll give you the hint. How about self-dual? Now, how did self-dual work? Self-dual. What does that let you do with the next and the negation?
Oh, swaps them.
Okay, so that would be what?
So next P or not next P.
Okay, so next P or not next P. Okay, so Adam, what do you think?
Would you do 3.59?
Right. Well, how about excluded middle, but now with P replaced by not P? Now, do you see that?
Oh, yeah. Should be true.
Yeah, which should be true. Is everybody clear how that worked? Okay, it's all these are using all those techniques that we used before. Is everybody good? Okay, so, and then falsehood. Now what do you suppose you'll do? You'll do, instead of excluded middle, what will you do? Which one do you think you'll use?
P equals not P.
Oh, you mean for false?
Oh, yeah.
Oh, yeah, yeah, I guess that's one way you could do it. Yeah, I was thinking about contradiction, but I think there's more than one way to skin a cat. All right, so those are the theorems for next. Now let's take a look at some of the theorems for until. Now here's the thing about until. Until is a binary operator, but now the thing about until, and we saw what informally or semantically, what does until mean? P until Q is true if, when does that hold? It holds in the state if what? If what happens? P until Q. What does that mean, roughly speaking? From this point on, what?
P is true.
P is true, and it's true, and it's...
And then Q is true, then P is...
Well, not necessarily... Well...
P
has to be true at every state in the future, now and in the future, and then when Q becomes true, and until Q becomes true, at which point it doesn't matter what P is at that point. So it's P until Q. So is everybody clear on that? All right. So the thing of it is that it's not, the thing that's interesting about it, that's way different from what we're used to before, is that it's not symmetric. Can you see informally that P until Q is not the same thing as Q until P? There's no, they're not the same kind of thing. Okay, so because the left-hand side and the right-hand side of until are like different, there's different concept associated with each one, then there's lots of axioms. So we have 8 axioms. First of all, next distributes over until. Next is pretty cool. It distributes over just about everything. All right, and here we have an expansion of until. So the expansion says P until Q equals Q, or P and next P until Q. Can you think about that? Does that make sense? I think it helps if you try to think how that makes sense. Because what are we saying? P is true until Q is true. So what does that mean? Well, either Q is true now, are you with me? Or P is true now and next P until Q. Does that make sense? I mean, I think if you think about it, it makes sense. And then here's the right zero, P until false equals false. So what are the zero laws? Do you remember the zero laws? What are the zero laws in propositional calculus? It's P or true, that's a zero law. P or true equals what? True. So this is 0. It's like P times Z, it's like something times 0 is 0. It's the 0. And what's the 0 for and? P and what equals that same thing? Yeah, P and false equals false. Okay, so these are the zero laws that we're familiar with. This is a zero. This is a right zero of until. P and why do you see why this is false? Because what does P until Q mean? P is true until what? Q is true, but false is never what? Never is never true. So P until false says because Q never happens. But that's an axiom, you know. And then the following 4 axioms describe how the until operator distributes over conjunction and disjunction. So look, we've got 13, 14, 15, and 16. And in each one of these, look at 13 has a disjunction on what side? Has a disjunction on the what? Right side. And P14 has the what? Disjunction on the left side. But now this is an equivalence and this is an applies. And then 15 has conjunction on the right side, and then 16 has what? Conjunction on the, wait.
Both of them have conjunction on both sides.
No, well, but this conjunction in parentheses is on the left side of U, of until. So are you with me on that? So this is left distributed and that's right distributivity. Yeah, so those are the 4 possible places for those to occur. And we have to specify those in the axioms to fully define the behavior of until. Since the recording of the lecture several years ago, this system has been modified by including some additional axioms in the definition of until and some other rearrangements of theorems and axioms. So for the remainder of this video lecture, the audio description of the theorem numbers will not match the video description of the theorem numbers, in which case the video numbering is the current numbering and it corresponds to the paper, A Calculational Deductive System for Linear Temporal Logic, which has been published in the ACM Computing Surveys. So here with the until operator, we have 3 additional axioms that were not present when the lecture was originally recorded, numbers 16, 17, and 18. And these are the ordering axioms, and we will not have much to say about those at this time.
This next slide shows 6 more theorems. The right distributivity of until over implies, which is similar to the distributivity laws for until over the conjunction and disjunction. We have the right zero of until, where P until true equivals true. We have the left identity of until, where false until Q equivals Q. And a very interesting one, idempotency of until, which is number 22 now. And then a very interesting until excluded middle, P until Q or P until not Q. So it looks like the old excluded middle from propositional calculus, P or not P. And then an unnamed theorem, number 24.
All right. So with that in mind, let's prove that until is idempotent. Remember, what is, let's review idempotency. What does idempotency, is conjunction idempotent? Yes or no? Little review here. Is conjunction idempotent? Remember what idempotent is? Because P and what? Equivals P. Yes, remember that? So that's idempotency. And what we see here is that until is idempotent. Let's prove it. So, Eva, you're up. P until P. 10. Expansion of until. So what would, if we expand, you have your equation sheet. If we expand until, what would this be?
Q or P.
Well,
Q or parentheses P and
yep.
X.
Hold on one sec. This is P until P.
Oh,
So it's going to be,
P or
oh, good.
parentheses
P.
and next parentheses P until P.
Yes, good. So P or P and next P until P. Is everybody good with this? It's actually expansion of U with what? Q replaced by P. Are we good? Does everybody remember how to do that? Use those. Okay. Okay, so now, man, here's an absorption law. Going to use an absorption law. What does 3.43b say? Do you remember the absorption laws? Vaguely? It's been a while. Got to get those cobwebs swept away up here for this absorption. Look, what does this absorption law say? We have a P and Q in parentheses, right? And then we P or that. Are you with me? And what does the absorption law say? If you have a P or a P and Q, that whole thing is just what? P. So now do we have an or, and then a parentheses and an and? Yeah, the whole thing just comes out P, and that's it. Good. We see how to do these? Yeah? So you go on your assignment for Monday, you go through. And so here's the right zero of until. That's interesting. Wait, I thought we had another right zero of until. Let's go back here. What's going on here? Look. Here's the right zero of until. What is the right zero of until here? It's false. But look at this. Isn't this curious? Oops. Isn't this curious? 18 says what? Not only is false a right zero of until, but also what? Yeah, so true is also a right zero of until. That's kind of strange. But it's true. Ripley's believe it or not. Strange but true. Right? And here's the left identity of until is, now what are the identity elements? What's the identity of and? Oh, we skipped the cameraman in our going around the room. Okay, so what's the identity of and? P and true equivals what? P, right, that's what it means to be an identity. So, all right. So false until Q equals Q, so false is the left identity of until. And here we have P until Q is stronger than P or Q because it implies it. All right? That's 20. All right, so let's do insertion. Insertion says Q implies P until Q. So here's the proof for that. P until Q. Okay, cameraman. 10. Expansion of U, of until. That's a pretty easy one to quote. Go ahead.
Q or parentheses P and next parentheses Q.
Right. Okay, so that's just right off out of 10. Okay, so Sam, what do you think? This next one is 3.76a, weakening. So, yeah, so which one, yeah, so if you have an or, P or Q, that follows from one of them. So which one do we want to have this follow? So here's the or, we want it to follow from Q, and it does by that, right? So that's it. Is everybody good? Okay. And here's a whole bunch of more. We have our own set of absorption laws. Look at this, 22, 23, 24, 25, 26. All of these absorption laws. We have P or P until Q equivals P or Q. We have P until Q or Q equivals. You see the general shape of an absorption law? You have this complicated expression and one of them gets absorbed and it makes it a shorter expression. Okay, so here's P or Q, P until Q. Oh, by the way, you guys, let's pause for a moment here. Look at 23. We need to talk about precedence a little bit. In 23, it says P until Q or Q, and there's no parens. My question for you is, where is the parentheses on this? Which has the higher precedence, until or or? Until. So anytime you see those binary operators, they grab, are you with me on that? They happen first. So that's why we had to put the parentheses in our previous one when we had hold on, let's go back here. Where were those, that set? Here, you see on 13, 14, and 15, and 16, we have to have the parentheses here on that. Because if we didn't, it would be just Q until R, and then it would be P and that for number 16. So just keep that in mind. Okay.
So if there were parentheses for this, it would be around the until.
If there were for example, for 25, if there were parentheses, they would be unnecessary, but we could put some unnecessary parentheses, and we could put it around P until Q. Yeah, exactly. And now, why do we have? In fact, thinking about 25, let's review our propositional calculus. Why do we need the parentheses around the P or Q on theorem 25? Are these parentheses necessary?
And or have the same precedence.
Because and or have the same precedence in our system, and so anytime you have an and next to an or, you have to have parentheses to disambiguate. Are we good? Because otherwise you don't know which one would happen first because they have the same precedence. And where there's no left to right, right to left, we don't mess with that. Is everybody good? Okay, so that's just the way that's the way we learned it. Okay, so here's an absorption, here's an absorption, here's a left absorption, here's a right absorption. All those absorption laws. You could prove all of those. You don't have to, but you could, given enough time. Okay. Now, the next one that we're going to learn, okay, so we did next, we did until. Now, check it out. Eventually, which is the diamond, is a special case of until when the left-hand side is true. So, eventually Q equivals true until Q. Now, let's think about that. Because what does P until Q mean? P is true until you reach Q, and then P doesn't have to be true anymore, right? So do you see that? But true is always true, right? So true until Q is the same thing as, well, as saying Q is eventually going to be true. Do you see how that works out, like in English or conceptually? I think it helps to think how these, think how reasonable these are. And that's the definition of eventually. So it's a special case of until. So that's our one definition. And now from that one definition, we can get all of these. Okay? Absorption of eventually into until eventuality, P until Q imply, so which one is stronger? If you know that P is true until Q is true, what do you know? If that's true, what do you know? Eventually Q is going to be true. Do you see? If you know that P is true until Q, then you know eventually Q. Does that make sense? You see how to think about these concepts? Okay? And here's the truth. You know, eventually true is true, and eventually false is false. Equivalence false. You can prove these. These are simple to prove. And then here's expansion. Now, what was our expansion of until? How did that expansion work? Expansion of until said P until Q was what? How did that?
Q or.
Yeah, it was Q, then it was or.
In parentheses, P and next.
P and next P into Q. So this is an expansion. This is how eventually expands. If P is eventually true, then what does that mean by expansion? That means either what? Either P is true now, or in the next state, P will eventually be true. You see how that kind of fits that expansion idea? See how neat this stuff is? I think this is really cool. And here, absorption of or into eventually, so P or eventually P. See, if P is true or eventually P is true, well, that's the same thing as saying eventually P is true. And that equivales, okay? They're equivalent. And here's absorption of eventually into conjunction. If you have eventually P, and you also have P, well, that's just the same thing as having P. And it's equivalent. Not just implies, but equivalent. All right, so let's do another one. I just have a few here for us to work through. Let's do weakening. P implies eventually P. Okay. Chloe, you're up. Eventually P. Now try not to cheat. I know you guys have access to the slides there, but anyway.
Yeah.
So now, what did we just see? Expansion of eventually?
It's P or next eventually P.
Right. So P or next eventually P. Okay, so Shane, now we're going to do weakening the consequent. And what does this say? You know, anytime you have an or, what does it do? Anytime you have an or, over here on 3.76a in the hint, it follows from one of them.
And we're trying to get it to.
And we're starting with the right-hand side, so we're trying to get it.
Trying to get a piece of P.
Yeah, so it just follows from P. Exactly. Is everybody clear on that? Is it coming back? I hope. Okay. So here's a bunch of others. Here's another weakening. Next P. So if next P is true, that implies that eventually P is going to be true. Do you see what I mean? So that makes sense? Next P implies eventually P. And look at this. What about this? If eventually, now this is an interesting one. If eventually, you're going to have eventually P. What does that equivale? What is it? You're going to eventually have P. See how that absorbs into itself? And what would be eventually P? Eventually, what would be eventually P? Eventually P. I mean, you have as many as you want. Stack them up, and they'll all collapse into one. Is everybody now? Remember that one. We're going to come back to that. And here, what can you exchange? See, next is really nice. You can exchange next and eventually. And furthermore, eventually distributes over or with equivalence, but eventually distributes over conjunction with implication. Do you see how now, does that make sense? In other words, if you have eventually P or Q, if eventually they're both going to be true at some state in the future, then that means you've got to have eventually, and you've got to have eventually P, or you've got to have eventually Q. And that's equivales. But on the other hand, what about and? If you're eventually going to have P and Q true at some state in the future, what does that imply? You're going to have eventually P, and you're going to have eventually Q. But not the other way around. Think about that. Okay, now the next one then is always. And check it out. Now, the always is kind of an interesting situation because not only do we have it defined here in terms of eventually, but we also have a few axioms that have to go with it. And when we were first coming up with this system, we thought, oh, that doesn't seem right. It seems like we should just define it this way and not need any more other axioms. But it turns out you need more axioms to get the precise, to define always. Okay, so here's the definition of always. Now think about this. The definition of all, by the way, do we prove 43, yes or no? No. Okay, because axioms and definitions are all unproven. They're all assumed. Okay, so what does always P mean? It means it's true now and it's true from here on out, right? J, clear on out, always. If we have always P, then what does that mean? What does this say? What is that the same thing as? What it means is you don't have what? Eventually not P. Now think about that. You don't have, because if you did have eventually not P, then it's not always. Kind of, it's an interesting way to think temporal. These things a lot of these things get, really technical. We don't need to learn the ins and outs of all of them, but just a few that we will use. And then 50 is pretty simple to prove. It's kind of the mirror of what? Of 43, right? What does it say? Eventually P is the same thing as what? No. Not always not P. Think about that. That makes sense. Okay. Oh, and here is our author's depictions, our author's slide 4.4 of duality. So he's showing a situation where we have not always A. So even if A is true, but it's going to be false sometime in the future and go back again, then it's not always A, even though A is true now. You see how he depicts that graphically. So let's do a dual of eventually. Whose turn is it? I think it's Shane's, is it? Is that right? It's not right? Really? I think it is. Okay, what about give us the definition. What if we use the definition 43, the definition of always, then always not P by the definition of always. So it'd be the definition with P replaced by not P. So not eventually not P. Excellent. Okay, Danny, what do you think? Oh, this looks pretty obvious. Do you know what the next one we're going to use? Sure, double negation. So now the cameraman can have this easy. What is this? Okay, good. And that's it. Boom. Are we good? Okay. And here's duality. He's saying not eventually A means that, here's an example of this is an example of not eventually A. So if we have not eventually A, what does that mean? A has to stay what? It has to stay false, right? So not eventually A is the same thing as, so not eventually is the same thing as always not A. See? Is that clear how that makes sense? And here's 53 through 60. We've got the truth of always true equals true, always false equals false. We have an expansion. We have some absorptions. Absorption. And here is another interesting one. Let's take a look at 60. Always obviously, well, that's the same, that equivalence what? Just always. And if you have always, 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 what do you have? Yeah, always. Yeah.
I know the theorems, but when it comes to like 53 and 54, if you have the right side, if you have true, why does that let you know that you're always going to be true?
Because that is the definition of true.
So if you're true, you're always going to be
No, true is always true.
Oh, okay.
Yeah. Do you see what I mean?
Yeah.
Because true is a constant, and it's at every state. Just think of it. You have an expression, true, and you have true at this state. That's true. True at the next state. Well, that's true. True is always true.
Okay.
Yeah, that's tricky. It's a good thing to think that way. I mean, that was a good question. So always false equals false, and then there's actually put your head around this. There's a meta-theorem. You know remember what a meta-theorem is? A theorem about theorems that says that that if E is a theorem, then always E is a theorem, and furthermore, if always E is a theorem, then E is a theorem. So it's kind of related to this, and by the way, that's listed later here. It's an interesting concept in temporal logic, linear temporal logic. Okay? And here we have 61, we have exchange of next and always, and we have some strengthening. Oh, these strengthenings, they make sense, right? Always P imply, if P is always true, then P is true now. Yeah? And furthermore, always P implies what? Look at all the stuff that always P implies. Always P, always P. I mean, it's really strong. It's really strong. If you say always P, that's pretty strong, right? And so always P implies P, always P implies next P, always P implies eventually P, always P implies next, always P, and etc. like that.
Recall that in propositional calculus, one way to prove that P1 and P2 implies Q is to prove that Q is true, and in the process of proving it, if you assume P1 in one step and then in another step you assume P2 as if they were theorems, and then when you get to the end and show that Q is true, you have proved that P1 and P2 implies Q. Now doesn't work quite that way in linear temporal logic, because if you prove Q and in the process of proving it you assume P1 as if it were a theorem and P2 as if it were a theorem, you have not proved that P1 and P2 implies Q. You have proved that always P1 and always P2 implies Q. And I've seen people make this mistake before in using temporal deduction. At any rate, we will never use this technique in this class, so it's an interesting thing for us to note.
And 48 is until implication law. If you have always P and eventually Q, that implies you have P until Q. And actually, it's too bad Ray is not here, because he is the one who came up with 70, 71, and 72. These are new theorems. This 69, temporal excluded middle. Now, what is our excluded middle that we're familiar with? P or not P. But now, what is the temporal excluded middle? Eventually P. So either you have eventually P, or you have always not P. Yeah, it makes sense? And what's interesting is this one appeared in the literature a lot, and we didn't. Here's temporal contradiction. Here's the other version of temporal excluded middle. This is new this year, by the way. This was not on the equation sheet last year. We just discovered these not too long ago. And then not P and eventually not P equals false. So there's a temporal contradiction, two versions of contradiction. What's our contradiction? What's our propositional calculus? What's our contradiction? P and not P equals false, right? So they can't be both true and false at the same time, right? And so this is saying It's saying if you have eventually P and not always P, that's false. Think about that. It all makes sense. And then here's some distributivity laws. And here's here's that proof meta theorem I was telling you. P is a theorem if and only if always P is a theorem. If P implies Q is a theorem, then eventually P implies eventually Q is a theorem. And if P implies Q is a theorem, then always P implies always Q is a theorem. These don't go the other way around. It's if this, then this. Whereas the meta theorem 81 is in both directions. And now this 49 is one we should think about. What's the difference between eventually always and always eventually? Now think about it. Eventually always. So eventually there's going to come a state in which P is always true. Are you with me? Eventually that implies what? That you're always going to have eventually P, but not the other way around. Can you think of a situation where you would have always eventually P, but not eventually always P? No, think.
P is true once, and then it always falls out of it.
But what's the counterexample? What's the counterexample for all? How would P behave? What's the counterexample for P to behave if you have always eventually P, but you don't have eventually always P? What would P?
Like oscillate.
Yes. Did everybody hear that? But did you hear what the point here? What did you say, Sam?
It oscillates.
Yeah, if P is up and down, up and down, up and down forever, if it's true, true, false, false, true, true, false, false, true, true, false, then what will happen? Isn't it true that you always have eventually P? But it's not true that you eventually have always P, because P is going up and down, up and down. Now, does everybody see that? That's a really important concept to get on the 49.
Now we have some really interesting absorption laws. Let's take a look at number 151 first. What number 151 says is that if you have always eventually P, and you just stick an eventually in front of it, that eventually just goes away. It's the same thing as always eventually P. And similarly, number 152 says if you have eventually always P, and you stick an always in front of it, well, that always just goes away. It's the same thing as eventually always P. Now, what's interesting about this is that we should compare them with the absorption laws for eventually and for always. So take a look at, recall number 50 here, theorem 50, absorption of eventually. What that says is that if you have an eventually P and you stick an eventually in front of it, it just goes away. It's the same thing as eventually P. And similarly, recall theorem number 72, absorption of always. What this says is that if you have always P and you stick an always in front of it, it just becomes always P. That always goes away. Now, these two theorems, number 50 and 72, combined with number 151 and 152, tells you that any string of eventually and always, you can have eventually, always, eventually, always, whatever long string of eventually and always, they will always collapse down to either always P or eventually P or always eventually P or eventually always P. Those are the only possibilities. The next four theorems show how always, eventually, and eventually always distribute over both conjunction and disjunction. So number 159 shows that that always eventually distributes over conjunction with an implication, and number 160 shows that eventually always distributes over disjunction, also with implication, whereas numbers 161 and 162, the distribution is with equivalence instead of with implies.
All right, now let's take a look at the concept of always eventually A. Now here's what how our author depicts it on slide 4.7. Always eventually A. So do you see, it's possible for A to oscillate up and down and for always A to not be true, but as long as it will always go back true at some point in the future, we do have, this is the meaning of always eventually A. Is everybody with me on that? Okay. And now look at this. This is our theorem 84. Distributivity of always eventually over and. Now look at what this says. It says always eventually P and Q implies always eventually P and always eventually Q. Now what did we say always eventually meant? Let's go back to the previous one. What did we say? What was kind of like the meaning of always eventually? It could be, as long as it's always going to be eventually true, it can be oscillating up and down, right? Are you with me? So what are we saying? What we're saying is if P and Q, if we have P and Q always going up and down, then what does that imply? That implies P has to always go up and down, and Q has to always go up and down. But what about the other way around? If P is always going up and down forever, and Q is always going up and down forever, does that mean that P and Q is always going to go up and down forever? No, not if one goes false, the other one goes true. So the implication is only one way. Now, is everybody with me on that? Do you see how that worked? And that's how he depicts it. This is how he depicts eventually always A1 and, always eventually A1 and always eventually A2, and shows this case where the and does not necessarily imply this one, going this way. Okay? And then here's another distributivity, only the one that we looked at before was always eventually. Now what is this one? This one is what? Eventually always, right? And here is his depiction of our 87, distributivity of eventually always over conjunction. So if you have eventually always the and, then that's equivalent to having eventually always the first conjunct and eventually always the second conjunct. Because there's going to be a time, namely the later time, when the and is going to be true. And these are actually pretty nice pictures of how to think about those. All right, good deal. See you next time.